Ever wondered how mathematicians and computer scientists tackle the chaos of complex systems? Today, we're diving into a groundbreaking approach using hierarchical graph lineages, a way to build and understand networks that grow in a structured, manageable way. Let's break it down. Imagine a graph as a map of connections, cities' nodes linked by roads' edges. Now, what if that map had layers? Like a pyramid, where each level is a group of cities, and roads mostly stay within or between adjacent levels. That's a graded graph, a structure that keeps complexity in check by assigning each node a level number. It's like organizing a skyscraper, where elevators only go up or down one floor at a time. But here's the challenge. When you combine graphs, say, merging two city maps, you risk a complexity explosion. Think of it like merging two skyscrapers. If every floor connects to every other floor, the result becomes a tangled mess. Researchers have been working on ways to combine graphs without losing control of their growth. Enter the skeletal cross product and box product, two new operations that let us merge graphs while keeping their spatial cost under control. The key idea: assigning level numbers to combined nodes in a smart way. For example, if one node is on level 2 and another on level 3, their combined node gets level 5, 2 plus 3. This additive rule prevents wild growth, like how adding exponents in math keeps numbers from spiraling out of control. But wait, there's a twist. Some connections between levels can still cause problems. Imagine a road that jumps from floor 1 to floor 3 in our skyscraper analogy. Those diagonal connections need to be trimmed, just like we'd remove unsafe shortcuts in a building. By carefully filtering these edges, we maintain the graph's structure while allowing it to scale. What's the big deal? These operations let us build graph lineages, sequences of graphs that grow in a predictable way. For instance, starting with a simple grid, we can thicken it into pyramids or bipyramids, each time keeping the complexity manageable. This matters for real-world applications, like designing efficient computer networks or modeling biological systems. The math behind this: it's all about universal diagrams and category theory, but think of them as blueprints for building these graphs. By following these rules, we ensure that even as graphs get huge, their growth stays controlled, like a tree that branches but never becomes a tangled jungle. Now let's shift gears. Ever wonder why your phone can recognize a cat in any pose, or why self-driving cars see the road so well? The answer lies in a mind-blowing intersection of math and AI, Lie groups and B-splines. Symmetry is key here. You know how a snowflake looks the same no matter how you rotate it. That's symmetry, math's way of describing patterns that stay the same under transformations. Lie groups are mathematical tools that describe how shapes and objects can rotate, scale, or shift while keeping their core properties. Think of them as the rules of how the world changes, like the physics of motion, but in math form. Now here's where it gets wild. B-splines are these smooth, flexible curves used in computer graphics to model everything from car designs to animated characters. But what if we could blend B-splines with neural networks? That's the idea behind B-spline CNNs on Lie groups. It's like giving AI a built-in spatial intuition, so it can recognize a cat whether it's tilted, stretched, or flipped, just like humans do. Traditional CNNs might struggle with these transformations, but this approach lets the network naturally account for them, thanks to the math of Lie groups. Here's the secret sauce. B-splines are like soft, stretchy bridges between data points, while Lie groups define the rules of how those bridges can bend and twist. By combining them, the network doesn't just memorize patterns, it learns the underlying geometry of the data. For example, when analyzing images, it's not just looking at pixels, it's understanding how those pixels relate under different transformations. This makes the network more robust and efficient, especially when dealing with complex real-world data. The results: in experiments, these B-spline CNNs outperform traditional models on tasks like image classification and object detection. They're also more energy efficient, which is a big deal for AI applications on phones or robots. But the implications go beyond images. This approach could revolutionize fields like robotics, where understanding spatial transformations is key, or medical imaging, where subtle variations in anatomy need to be detected accurately. So why does this matter? It's not just about better AI, it's about smarter AI. By grounding neural networks in the math of symmetry and smoothness, we're building systems that learn like humans do, by understanding the rules of the world, not just memorizing examples. Now let's explore another frontier: topological approaches to deep learning. Imagine taking a chaotic dataset, like a tangled mess of strings, and using math to map its shape. Topology helps AI see patterns hidden in the chaos, like spotting a mountain range in a jumble of dots. It's like giving AI a new pair of glasses to see the world in 3D. Then there's transfer learning, the AI version of learning a skill to master many. Think of it like teaching a dog to fetch. First, it learns to recognize objects, then that skill helps it learn new tricks faster. This way, AI can apply knowledge from one task to another, saving time and resources. But here's where it gets wild: category theory. This isn't just math, it's a universal language for equations. By translating complex ideas into simpler structures, researchers are building neural networks that are easier to understand and more reliable. It's like giving AI a roadmap through a maze of abstract concepts. And let's not forget multigrid methods. Borrowing techniques from fluid dynamics, these approaches let AI tackle problems in stages, starting with the big picture before zooming in on details. It's like solving a puzzle by first arranging the edge pieces, then filling in the middle. What's the big idea here? These techniques aren't isolated. They're part of a movement to make AI mathematically elegant. Whether it's through topology, transfer learning, or category theory, researchers are building systems that are smarter, more efficient, and easier to trust. From decoding 3D shapes to automating AI design, these breakthroughs are already shaping the tools we use every day. The future of machine learning isn't just about power. It's about precision, adaptability, and clarity. Thanks for watching. If you want to explore any of these concepts deeper, check the links below. Don't forget to like, subscribe, and join the conversation. Until next time, keep wondering, keep learning.